Now let's talk about cryptography, because this is an incredibly important part of how blockchains work and something you really have to understand if you want to become a blockchain developer. So why is it important? Well, if you think about the word cryptocurrency, that root crypto comes from the word cryptography, which is a pretty good indication that it's incredibly important to how these blockchains work. So let's see how. So what is cryptography? Well, in essence, it's really just hiding information so that you can transmit that information and other people can see it and they can't understand it. So basically, it's the practice of taking information and encoding it so that it's hidden and other people can't understand it, and then being able to decode that information so that you can understand it, or at least verify that you can encode the same information twice to get a match. So cryptography is used in blockchains. It's used in lots of other areas of computer science, and it's even used outside of computers. Okay, so we're going to look at, the Wikipedia entry here so you can get an analogy about, what cryptography really is, even outside the concept of computer science, so that you can then apply it to computer science and blockchain. So cryptography, or cryptology, all right, is the practice and study of techniques for securing communication in the presence of adversarial behavior. So more generally, cryptography is about constructing and analyzing protocols that prevent third parties or the public from reading private messages. Okay, so this has existed for a very long time, even before computers. You can see this machine over here that essentially, determines how things are going to get randomized so that you can transmit messages without someone finding it. This is the famous Lorentz cipher machine used in World War II to encrypt the communications of the German command. And here you can even see it presented in book form, or you could safely transmit around this text, which doesn't really make sense if you're just looking at it, because this has been encrypted, okay, and printed out. And what you need is something called a cipher, essentially, to decode this information so that you can understand it. And that's basically the encryption algorithm. Is the cipher lets you decode this information so that you could say, okay, well, this letter needs to be translated to this letter needs to be translated to that. And then as soon as you have that key, essentially, you can make sense of the text as it's originally intended. So at the core of any cryptographic implementation, whether it's in a book, whether it's in a mechanical device, a computer, a blockchain, whatever, is an encryption algorithm. Okay, so this is the process of taking raw information, whether it's text, whether it's a user password, whatever, and then running it through an encryption algorithm to create some sort of digest, okay? And then having some sort of cipher potentially to decode that information. You may or may not have that. But the whole idea is that you can take raw information, run it through an encryption algorithm, and create a digest, and then you can safely pass this digest around without anyone being able to understand what the raw information is. So the main way we do this with computer science and also in blockchains are something called hashing functions. These allow you to take in any information that you want to and create these hashes, okay, that are digests, which are encrypted information. So let's just kind of play around with a hashing function to see how it works. Then we'll talk about the properties that you need to understand about hashing functions, and then we'll see how it applies to blockchain. All right, so here on my screen, I have pulled up a bunch of different hashing functions that I can choose from. So these all have specific names. You can see ones here called SHA-256. This is one of the most popular hashing functions. So what is this function? Well, it's literally just an encryption algorithm that works the same way every single time that my computer can essentially run to encrypt information. And so whenever I click a different one, like MD5, for example, it just runs a different unique algorithm. Okay, so let's just observe its behavior and then describe how it works after that. So essentially, I can put in any text that I want here. I can just say, hello, world. Okay, and then you can see that it encrypts this information and gives me this output right here. Okay, so you can see I can put in a lot of text. I can say, hello world, welcome to Dapp University. And it's giving me new information every single time, and it's always the same length. Okay, and so anybody who has this cannot understand what this is, but if anybody had this and then ran it through the same encryption algorithm, they could always produce this same result. All right, so let's look at the properties of hashing functions and how they work before we can talk about how we use them inside of blockchains, okay? So I'm just going to give you a primer on this, just as really about the conceptual properties of hashing functions. We're not going to get deep into the math because you don't really need to know that in order to become a blockchain developer. This is just going to get you started so that you can, start with a strong conceptual framework. So all the hashing functions that we saw a second ago on that website embody this property, where essentially you can take input text, you can see that in the column here, you can run it through this cryptographic hashing function, and then it produces a digest. So the input is the human readable input, or whatever input you want to, and the digest is the encrypted information, and the yellow part's the hashing function itself that runs one way. So let's look at the properties of each hashing function. The first property is that they have a fixed range. So what does that mean? Well, essentially, no matter what input you stick inside the hashing function, it's always going to produce a digest of the exact same length. So here you can see we just put in 3 letters of Fox. So run through the exact same, cryptographic hashing function. This puts out, 4 groupings of 4 here. 1, 2, 3, 4, 5. Okay, so that's 20, 40 characters. All right, and that's only with 3 letters. But it doesn't matter if you put in a full sentence; it still puts out the same number of characters. That's what fixed range means. Next, hashing functions are deterministic. So that essentially means every time I put a certain input into a hashing function, it's always going to produce the exact same output every single time with no variation. So every time I put the word Fox into this hashing function, it's always going to produce this exact same digest over and over again. That's critical because if you ever want to compare information by running it through a hashing function, you need to make sure that it works the same way every single time. So the next thing is that hashing functions are discontinuous. That means that even the slightest difference in the input information generates a wildly different output, okay? And that's really important because you don't want to be able to guess what the potential input is. So for example, on this word Fox right here, if I just changed one letter, it would completely change the digest. Like it would look more like this rather than just changing one letter in the digest. Similarly, if I changed you can actually see the difference here. So you can see the red fox jumps OR, so OVER versus OUR. Just by changing this one letter, you can see how different these outputs appear. So the next properties are they're non-invertible. Okay, so essentially, if you have the digest, there's no way that you can reverse engineer this to get the input. So if you have the output, you can't get the input. That's important because you want to be able to pass these hashes around, okay, without being able to run it back through the same hashing function to get the input. So how do blockchains use cryptography? Again, if these are such a core part of how blockchains work, then why is it important? Okay, so there's lots of ways for the accounts themselves. Okay, if you ever see a user's private key and a public key, that's heavily reliant upon cryptography. We use cryptography whenever we are adding new transactions to the blockchain with our consensus algorithms, okay, and also when we are chaining blocks together. So let's look at and a whole lot more, but let's look at a couple of these examples so that you can see how cryptography is important. So one example is whenever blockchains are achieving consensus. So in a previous section, we talked about consensus algorithms. So if you haven't checked out that video, definitely do that. But in that video, we talked about proof of work and, how this was the consensus algorithm for Bitcoin and how it's the original consensus algorithm for Ethereum. So basically, whenever somebody submits a transaction to the network and the nodes are going to include that transaction to a block to add it to the blockchain, that you have a miner who's going to get paid to do that. And they do that through the consensus algorithm of proof of work. And so a quick recap, essentially what happens is you have these miners that compete to solve a cryptographic puzzle, all right? And the miner who wins that puzzle is the one who gets selected to include the block into the blockchain, and they get paid a reward for doing that. That's their incentive. Now, cryptography plays a strong role in this because essentially in proof of work, what happens is the blockchain essentially creates a nonce, which is just a random number. And all these miners have to guess what that random number is, okay? And so essentially in that case, they get an encrypted version of this nonce hash that gets run through an encryption algorithm. And essentially what the miners are doing is, this is an encrypted number, so it's safe to produce this and put it out there on the entire blockchain because no one knows what the answer is. The nonce has been encrypted. It's out there for the miners to know about, and they have to guess the nonce. So they see the encrypted information, but they don't know what the actual, unencrypted nonce is. So they essentially, what they do is they take a bunch of random guesses and they run them through an encryption algorithm to see if they can match the output. Okay, and if they match the output, then they know that they have found the right answer or a valid answer. It's not always one answer, but a valid answer. And then the network can accept that, and then this miner can be selected as the winner to include this back into the blockchain. And again, that's just under the proof of work consensus algorithm. Okay, so another way that cryptography is used to secure the blockchain, and this is really fundamental to how blockchains work, is that we use cryptography to actually construct the blockchain and chain blocks together. So remember that in the previous sections, I talked about how the blockchain is comprised of transactions. All right, anytime you do something on blockchain, you're creating a transaction, and those transactions are grouped together into bundles of records called blocks, which are chained together to make up the blockchain. So inside of each of these bundles, inside each of these blocks, there's this thing called a block header, okay? And that block header actually gets a hash, which is stored in the next block. So if you think about it this way, if you take all the information in block 10, right, all the transactions that go inside of it, any other information about this block, and then you generate the header and you run it through this hashing function, then you're going to get a digest, like looks kind of like this, and that's going to get stored here in this previous hash section. And then for block 11, whenever you add all the transactions and get all the information, you're going to repeat that process again and add it to block 12. And so if you think about it, block 12 includes all the information that existed really from block 11, okay? And then block 11 includes all the information from block 10, and then so on and so forth, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, all the way to the genesis block in the chain. So if you think about it, each valid block currently understands all the history of every single block on the blockchain, okay? And so if you remember our properties of our hashing functions, they are discontinuous, which makes it really, really hard to change anything about the blockchain's history, because if you went back in time and changed a single piece of information, then you would mess up this hash that goes into block 11 in the blockchain, and this problem gets much, much harder the more blocks you add, because you'd have to go back in time and change, if you change one hash, then you're going to knock every single domino down that chain. You're going to affect the next hash, the next hash, the next hash. And so the larger the chain becomes, the harder it gets to go back in time and actually change anything, because you're changing the entire history and you have to change every single block after it. So that's a huge way in which cryptography secures the integrity of the blockchain so that nobody can actually tamper with the history and affect the current state of things, because we basically hash every single block and contain a reference to that hash in each subsequent block. Now, another way in which blockchains use cryptography is to generate accounts, okay? So again, in previous sections, we've talked about how, a really unique value proposition of blockchain is that you are a user of the entire network, not just a user of an individual application. And so to connect to the blockchain, you need an account. You need something called a key pair, which gives you a private key and a public key, which turns into your address. Okay, we'll see that transformation here in a minute. But essentially, your private key is sort of like your password on the blockchain, and your public key is kind of like your username, or really your address is, okay? So you can think about this, in a very loose way about like username, password. And the cool thing about this is you can actually generate your username from the password, and that's where cryptography comes into play. So in order to prove that you are you on the blockchain, the only thing that you need is a private key. If you have this written down somewhere, or that you have memorized this, which I highly doubt, then you have access to whatever wallet this controls. Okay, it's like a password. All right, you don't even have to know the username. You'll see why here in a second. Now, quick disclaimer: anybody watching this video should never, ever, 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 ever use this private key, because the whole point is if you have access to this, and you can control any type of money that's controlled by this account. Okay, so quick disclaimer here. But anyways, this is an example of what a private key looks like. And so you can use this as a password to generate a public key through encryption. And the encryption in the public key is going to be like your username. So essentially, you can get your public key with the private key like this. You can take the input with the private key we saw in the second or in the last slide here, and you can run through a hashing function, okay? And specifically, you can run it through the elliptic curve digital signature algorithm, so ECDSA. This is a specific encryption algorithm. And whenever you put in this information, it's going to generate a public key that looks like this. That's going to be, like your username on the blockchain. Now, if you have used a blockchain like Ethereum before, maybe you've had a MetaMask account, you might see that this looked nothing like the MetaMask address. Or, if you looked at Etherscan and you've seen smart contract addresses or any user account, this doesn't look anything like that. Well, that's because this is the public key. It's not the actual user address. So how do you get the user address, which is really more like your username? Well, there's an additional step. So you take the public key, all right, which you saw a second ago, then you run it through another hashing function, okay, which is KCAC256. There's lots of ways to pronounce this. That's how I pronounce it. And then you take the last 20 bytes of the digest here, okay, and then you add 0x to the beginning of it, which turns it into something that looks like this. So this might look a lot more familiar if you've ever seen an Ethereum address or another blockchain that uses the same encryption scheme. Then this is what looks really common, and that's how you get there. Okay, so we've seen how private keys work to get the public key, but let's look at another really critical function of private keys and why you never want to share it with anybody and why they're so useful with blockchain. So anytime you do a transaction on the blockchain, let's say that you're going to send cryptocurrency from one account to another, you need a wallet to do that, and then you connect to the blockchain, you create a transaction, and whenever you do that, you sign the transaction with your private key, okay? You sign it with your private key, and that creates a signature that goes into the transaction that gets mined and included into the blockchain, assuming you're using proof of work, okay? And this is how the blockchain knows that you are authorizing this transaction. Let's say we're using Bitcoin, for example, and you want to send Bitcoin from one account to another. Well, you have to create a transaction and then sign it with your private key to tell the blockchain, yes, I do intend, me personally, the owner of this private key, intend to move funds from one account to another. Because if you didn't do that, then somebody else could essentially just create a transaction if it didn't require a signature that says, hey, move funds from this account to the other. And that's not going to work. So you have to authorize every single transaction on your own behalf. And that's why the private key is so important, so that you can sign messages to create that digital signature. And that digital signature is the only way to verify that you are you, the person that's, authorizing this transaction. So all of this is part of, the digital signature scheme for blockchains. They all work slightly differently, but they're all a part of what's called public key cryptography. And another name this goes by is asymmetric cryptography, okay? Because basically any type of cryptography where you have a private key and a public key, and then you can safely send information around like that, is got to do with this asymmetry or public key cryptography. So let's see how that works, because that concept is really important to how blockchains function. So in this case, let's look at how a digital signature works from kind of an abstract way before we look at it how blockchain works. So let's take an example of Alice and Bob. So Alice wants to send Bob a message and verify that she is the person who sent that message. So Alice has a private key and a public key, okay? So essentially, what can happen here is that Alice can sign a message that says, hello, Bob. She can sign it with her private key, and then she can get two pieces of information, the original message, hello, Bob, and then this digital signature that's really just a digest of this message, okay, hello, Bob, encrypted, that she encrypted with her private key. And she can send the original message plus this digital signature to Bob, okay? And now she retains her private key, but she can also give Bob her public key, because that's okay. That's like her username, okay? In fact, that might even be in the message, like, who's this message from? Oh, it's from this public key. This public key belongs to Alice. And then if I have the message and I have the digital signature, all I need is the hash of the signature plus Alice's public key, which is safe for me to transmit around. And with these two pieces of information, I can't decrypt this, but what I can do is verify that it was signed by Alice's private key, that this private key is the only one that could have possibly created this special signature hash. and therefore I can know that this message, hello Bob, actually came from Alice's account, because only this private key could have possibly created this exact output. And you can know that through public key cryptography by just having these two safe pieces of information that are okay to pass around. So let's see how that works on a blockchain. Let's say that I want to send some cryptocurrency from my account to yours. In this case, what I would do is I would create a transaction, okay? And then I would sign that transaction with my private key, okay? And then I would send that transaction to the blockchain itself. And so that's going to contain two pieces of information: the basic transaction instructions, which say take cryptocurrency out of my account and put it into your account. And then it's also going to contain my digital signature, which is just a hashed signature from my private key. And whenever the blockchain receives it, okay, the nodes on the network can actually verify the instructions that are valid that say take cryptocurrency out of one account and go to another. And they can also verify this digital signature that it was in fact, generated from this private key, because it knows the from address, it knows the public key or the address derivation, okay? And then it can compare the signature with the public key with public key cryptography to verify that the person sending this message actually is authorizing the debit of cryptocurrency out of their account and credit to another person's account. So whenever the blockchain verifies this, it can, include that transaction into a block, and then it can get included in the blockchain. And that's how we use public key cryptography to do that. All right, so that's an introduction to how we use cryptography for blockchain. So we've covered a lot in this video. Again, you don't have to be an expert in every single one of these topics in order to do well as a blockchain developer. You don't have to understand all the math behind it and everything. It's just important to get some of these basic concepts down so that you're comfortable working in a blockchain environment. So if you need to rewatch this video and kind of re-examine some of those concepts, they can be kind of hard to wrap your head around initially. That's okay. Or you can just skip ahead and continue working through the lessons and revisit this later when you need some reinforcement. So that being said, let's jump in the next video.